All right. Welcome back to the final session of the conference. The first speaker is going to be Jeanie from Ohio State. She's going to tell about superconductors and insulators in flat bands or flatland.
All right, thank you. Right, so first, of course, I have to thank the organizers for putting together this wonderful event. This is definitely one of the best conferences I attended this year. I was definitely the happiest. Also, I guess, and thanks everyone for staying to the end. The problem with being the last session is that, oh, the jokes about Allan has already been used. So I have to work hard to come up with new jokes last night. And also the many sentiments have already been expressed, but I think Allan can hear it again. Okay, so I'm going to tell you about superconductors, insulators. And so I've decided to add this title to screen or not to screen. This similar to Emmanuel Tutuk's talk, to twist or not to twist. Okay, so all right, so just to start to say my connection with Allan. Actually, I don't remember when we first met Allan. I think it would be 2009 plus minus 1 year, roughly. I think we co-authored 6 papers together. And there's one in preparation, which has been in preparation for 10 years. So you know that the project with Allan, you say you never finishes. You keep on working for decades. So that's wonderful. So, all right, so what I learned from Allan, or what I've received from Allan, so it's a tidbit, the etymology of MacDonald. So I was told this means, Mac just means the son of Donald. And the difference between spelling with of MAC and MC is, I think there's some time in the history of Scotland where I have the war with UK, with England, and before that was spelled with MAC. Allan can correct me if that's correct. Okay, so there's a little tidbit, but. Okay, so of course, Allan is a wonderful, wonderful scientist, great, wonderful to its function of scientific knowledge, insight, and vision. And of course, also support kindness and generosity. I have learned from Allan how to stay calm when facing referee 2 and 3, even though my blood is boiling. And Allan's always provide this anchor of like sea of calmness. Above all, I think whenever I talk to Allan, he reminds me of the wonders of physics, reminded me when facing referee reports, rejected proposals or whatnot, why I became a physicist in the first place, to explore nature, to understand the wonders of nature. So I think that is a really wonderful experience. All right, so thanks, Allan. I think I can speak to everyone in the room for everything you have done. And also, I think we want to thank the people who checked out all the physics books, except Kittel in 1973. So for those who were not at the banquet last night, Allan said he went into condensed matter physics because all physics books were checked out except Kittel. So I think we owe these people a lot of big thanks. I'm sure Allan will do well no matter what, but condensed matter physics will suffer great loss if some other books were left. Okay, so all right, so lessons learned by working with Allan. So we want to listen to Allan because Allan is almost always right. Okay, so this is like a proposal we submitted with Allan in April 2015. Well, this is some writing from Allan. A clear gap of functionality is absence of 2D magnetic materials, et cetera, Needless to say, this proposal was not funded. But of course, you know, we probably should have stuck, right? And still don't, sorry, then we, maybe we can you know, try to discover something about 2D magnets. Okay, all right, so if a student funding agency tells you otherwise, you go number 1. And I probably want to say try harder. Okay, and then another thing we learned is, of course, Allan is a great collaborator, we know that. And sometimes maybe too great. What do I mean by that? This is the conflict of interest table from Allan. With one of the proposals submitted, you can see it's like 476. Number of collaborators who are conflict with Allan. So after this, I was like wondering anyone else left in the field to review the proposal. So needless to say, this is also declined. Okay, but anyway, but this says that the number of collaborators from Allan is just how great, wonderful collaborator he is, and inspiration to us all. Okay, so all right, so that aside, so let me just tell you a little back to the topic, the title of the talk. Flatland, we know the Flatland, it came from this book, published in the 1880s. We talk about square who lives in the flatland with lower, higher dimensions to open up different perspectives. Little do we know, now we know that flatland itself is very interesting. So right now, I actually came from a superconducting nanowire community. So actually, in fact, I came from line land back to the flatland. Okay, so and another reason flatland is because this is I came from Columbus, and that is very, very, very flat. Okay, so now we'll try to be brief about this part. So how do we generate flat band? This is already seen many times during this conference. We can generate by magnetic field from Landau levels. We have kinetic energy currents is completely flat. I think this is a paper I dug up from I don't know if this is earliest paper from Allan on quantum Hall effect, but talk about quantized. This published in '83, quantized Hall conductance in relativistic 2-deck. So this is very, very, this is years before, actually 20 years before graphene was discovered, right? Was experimentally isolated. Of course, we can also make flat band by stacking. Okay, so that's what I'm going to. That brings me to the sort of brief outline of the talk. The first part I'm going to talk about mostly old work. So this is stacking, how we what we look at the flat band in suspended rhombohedral field layer graphene. The second part of the talk, I'll tell you about how a very recent work and published, tuning superconductivity in twisted bilayer graphene by maximizing screening. And therefore, so this is a little bit mirrored with Emmanuel Tutuk's talk, to twist or not to twist. So this is no twisting. This is twisting, also to screen or not to screen. That is the question. Okay, so so this first part of the talk, so this is a series of my very wonderful graduate students, Hairo, Wenzhong, Yongjin, Shi, and Kevin. And so the theory was done by Fan and Allan. Okay. Okay, so you probably already heard some of this. So this is rhombohedral stacking. And so if you stack up graphene layer by layer with rhombohedral graphene, then these stacked, so Fan has mentioned this yesterday, the stacked atoms hybridize to form high energy orbitals. So basically left with sublattice A from first layer and sublattice B from the top layer. As a result, this is a very, the energy, the dispersion of this field layer graphene actually goes as momentum to the power n, where n is the number of layers. So in 3 layer and 4 layers, so this is cubic and this is quartic dispersion. So there's a lot of, so this started works back, the theory work started back in 2008. Experimental work, I would say, started with this Amir Jacobi's work in 2010. So the question started with about what is the state at the direct point in bilayer graphene, because the band is flat, flattish at least. So there's a lot of debate, and so this is a work from our group, and this is some of the work from Allan's group. So there's a big, so there's a lot of theoretical debate. And so what we do is we have this suspended graphene. This is before the HBN becomes was demonstrated by Columbia group to be a really great substrate. This is how we make very, very clean samples. We suspend graphene. We have a backgate and we have a suspended topgate, which is this like the air bridge. And we current anneal the samples so that they're actually very clean near the charge neutrality point. And so then this is what bias spectroscopy measurement. This plots two-terminal conductance, or differential DI/dV. versus electric field, which is horizontal axis, and source drain bias, which is vertical axis. This is done at charge neutrality point. So this blue region is actually very low resistance, low conductance. So take a line trace here. So we have close to 0. This is like megaohms. And then we have an large electric field, the conductance decrease. So first increase and then decrease again. And if we do a vertical line cut, now what we see that, for example, at the charge neutrality point and 0 electric field, we have seen the conductance versus bias actually looks like some sort of spectroscopy measurement of a gap state with the sharp peaks. So what we conclude from this is that this, okay, so it looks like the density of state of gap state. This is intrinsic gap state of 2 MeV, and this gap can be closed by electric field either polarity. Okay, so following this, we have, so we go to 3 layer and 4 layers, very similar phenomena, except energy scale just get progressively larger. For example, in 4 layer, we see the gap is about 40 MeV. The transition temperature, transition between the conductive and insulating state happens at about 35 Kelvin. And in all these devices, the gap state can be, we can kill the gap state by going to larger density, a larger displacement field, or an in-plane magnetic field, so in-plane magnetic field. Okay, so this is a 4-layer sample. You can see very, very sharp peaks. And again, about 80 millielectron volt. So this is a theory. Theoretically, the possible states. So these are possible states. Basically, you have spin and valley, and then you have 2 layers. How do you put the different spin and valley on the layers so you can? So this will give you either anomalous Hall state, you can have quantum spin Hall state, or you can have layer anti-ferromagnet. So what we have our results, since we show is gap insulating. So this basically eliminates the Nimitti order, the anomalous Hall state, and the quantum spin Hall state, and this leaving us with and the fact that the electric field or either polarity can destroy this state. So this removes the quantum valley Hall state, and so this leaves us with this layer anti-ferromagnet, meaning the so the top and bottom layers are obviously spin polarized. The middle layers, you have more than 2 layers. The middle layer are just sort of inert and they don't do too much. Okay, so this is a phase diagram. We think so so it's a layer anti-ferromagnetic state. If we have, it's a ground state at 0 charge density, 0 electric displacement field, 0 magnetic field, and you apply an in-plane magnetic field. Let's go to spins will start to cant. Eventually, this will be give us this magnetic state. And you will apply a large displacement field. You push all the electrons in one layer. This is on the top or bottom layer. So this will give you a quantum valley Hall state. Of course, we know that recently this has been this similar layer anti-ferromagnetic state at charge neutrality has been observed on graphene HBN and by Longjuice group, for example. And this and of course now also quantum anomalous Hall state, and all that very interesting stuff. Okay, so that's so that just shows that there's a lot of interesting phases possible in this system. It just depends on whether you screen or not. So it looks like when we suspend the sample, we minimize screening. So the Coulomb interaction is largest. So at the charge neutrality point, we got the layer anti-ferromagnetic state. Okay. So when you put devices on HBN, so this state is only observed in 5 layers because it gets you have more screening, but so the band also becomes flatter in a thicker sample. Okay, so all right, so this now if we go to small doping in this these suspended devices, and so charge neutrality point, we have an insulator. If we dope it slightly, we actually see very prominent magnetic hysteresis. And this hysteresis is dependent on density, so it's dependent on where we go, and also temperature dependent. It really disappears at about 5 Kelvin. So this tells us we really have intrinsic magnetism when we have a lightly doped suspended field layer graphene. Okay, so this we collaborated with Mattia Calandra's group, which shows that the electric field breaks inversion symmetry and induces spin splitting. So let me just be roughly brief. And now, of course, we know this recent marvelous works from this group on rhombohedral field layer graphene. So we have, so we also like to return to this system, and but probably with a slightly new twist, meaning that we want to put this on a slightly different substrate. That is, brings me to the next top of my talk. Okay, the next topic, which is actually a substrate with more screening. I want to see, what happens to all these phases. Okay, so so this again, how to generate flat band. Of course, we know twisting. This is so we already seen many of this. Rafi already gave a really nice talk about this, how this came about. Okay, so I just want to point out it was published in 2011. And so I know there's a lot of experiments in this work. I think, for example, Eva Andre already actually, in fact, started doing this even before this paper was published. I want to say that my group also tried with suspended samples, but it was actually turns out to be a sample. It was difficult to look at this. So we sort of gave up. We didn't publish anything, but this just reminds me of rule number 1, listen to Allan, right? So but I'll tell the students, try again. Okay, so of course we know this was experimentally realized by Pablo's group in 7 years later, and I will say that the rest is history. And so we have we are working on this, but today let me tell you about recent work, how we twin superconductivity in this system by maximizing screening. So this work was led by my student Xueshi Gao. It's a joint project with Mark, and the theory was given by Paco Guinea's group. Of course, this guy's Taniguchi group provided the HBN samples. Okay, so the driving question is what is the pairing mechanism of superconductivity in twisted bilayer graphene? So a lot of different proposals. I think Allan's proposal is among there somewhere. Okay, and then so the question is, I think that really comes to whether it's phonons, non-phonon, maybe electronic signature. I know Shankar here, and Shankar says 99% of the time it's phonons, so never bet against phonons. Okay, so okay, well, we'll see what experiments say. Okay, okay, so okay, maybe let me just say that what happens? How about electron-electron interactions? So we can change the interactions by either changing the dielectric constant. So there's changes on side interaction. We can change also the bandwidth by change, which depends on the angle. So experimentally, this has been addressed somewhat, I would say, right? So for example, there's two papers from Dima Avatov's group and also Andream's group, where they place a metallic gate very close to the twisted bilayer graphene. The distance is between 7 to 30 nanometers. And so what they see is that the correlated insulating state weakens or disappears. Okay, so for example, here, this is weakened, but superconductivity survives. Okay, so from these, what they conclude is that the correlated insulating state and superconductivity are competing rather than parent-child. For example, there's some thought about maybe the superconductivity is obtained by doping the correlated insulating state. Okay, so the conclusion is that they are competing states. I think they are actually very careful in reaching that conclusion. But if you want to take one step further, that certainly some of the theory has done, is that maybe you want to take this as evidence of superconductivity being independent of electronic interactions. But I want to argue that I don't think you can really reach this conclusion based on the data presented in these papers. This is because they are different samples with very different mobility, different trace angles and strain. So every sample is different. And so it's actually hard to, I would say, challenging to reach a conclusion given there's a lot of uncontrolled factors there. And they can all affect where, where the superconductivity and insulating states appear. Okay, so what we do here is actually we put twisted bilayer graphene on this strontium titanate substrate. They're separated by a thin layer of HBN, which is 3 nanometers. This particular device is right at measuring angle 1.05 degrees. Turns out strontium titanate has a large dielectric constant. So what here we have, I should also say we also have a top gate, which is graphite, and we're separated from twisted bilayer graphene with a thick HBN. So here we're plotting the resistance as a function of top gate voltage and back gate voltage. So this red, this very resistive state. So this is band insulator. So this is +4. This is -4. 4 electrons per or 4 holes per Morris unit cell. This is the charge neutrality point, a global charge neutrality point. This is correlated insulating state at +2. Okay, and this really dark region is basically superconductivity. So if you look at this this phase diagram, right? So one feature is that immediately it's different from right, if you have HBN back gate and top gate. So HBN dielectric is that or silicon oxide dielectric is that these features are curved. Okay, meaning that the ratio of dielectric coupling, capacitive coupling between the back gate and top gate are changing. So it's not constant changing. So top gate is very, just HBN, and we also can verify this by Hall resistance measurements. Top gate is very well behaved. The top gate is just linear. So which means that the back gate, the dielectric constant of the STO is changing. Okay, so we can estimate that the dielectric constant ranging from 8,000 to 25,000 in the experiment. So being larger near the top and smaller nearing the bottom, on the bottom right. Okay. And so now with this, now we can, what we'll do, we're going to stay at 1 back gate voltage, and then we're going to sweep the top gate so that changes charge density, and we can go through all the superconducting, correlated insulating state, and band insulating state at each different dielectric constant. Okay, so this is what we did. So this is, for example, at back gate voltage of 15 volt, we see this, this is a superconducting phase. And then this -5 volt, this is a superconducting phase. So here the, so we're outlining, so there's a superconducting dome. Okay, so this shows the entire superconducting dome is tunable depending on the dielectric constant. Okay, and so if now we're just replotting these domes at different back gate voltages, their extent in top gate. So this is TC, this is the critical temperature, and this dome, and this is critical magnetic field dome. And this, and the plot on the right, we're plotting the maximum, we're just picking up the maximum value of the transition temperature, and then we convert the back gate voltage and top gate voltage, convert that to the electric constant. And so this is what we see. Okay, so what we see is that the TC and BC are suppressed by increasing the dielectric constant, which means that increasing the screening or weakening electronic interactions suppresses superconductivity. Of course, I would love to say that this means that, does that mean this, the pattern is driven by electronic interactions rather than phonons? We probably cannot reach that conclusion yet, but because electron phonon coupling can also be affected by screening. But what it does say is that the electronic interactions is important, right? Maybe also perhaps in addition to phonons, facilitates screening or something. Okay, waiting for theorists to chime in. Okay, so how much? 1 minute. Okay, so very briefly, we also have another sample that's a very large angle, which is 1.45 degrees separation from, it's about 4 nanometers. So here, interestingly, this is really large angles, but we actually see superconducting pocket here. So this is definitely weaker superconductivity. So TC is about 0.4 Kelvin. But we actually do see superconductivity here. It's also kind of a little bit stronger here and a little weaker up here. Okay, so what we so this work is now posted on the archive, and I also want to say there's a work from Bagugan group from Singapore, where they have put it's put 2 twisted bilayer graphene on top of each other. One of them is almost like a Bernal bilayer. The other is magic angle twisted bilayer, where then they can tune the Bernal bilayer in and out of the gap. And so what they reach the same conclusion in with us is that if we increase the screening, that seems to suppress superconductivity in twisted bilayer graphene. I also want to say, Emmanuel Tutu already talked about earlier that they have similar setup, but what they look at is correlated insulating state. So they did not see superconductivity in this setup. Oh, maybe yet. Okay. Okay. So the summary, we want to say that it looks like the interactions have played a double-edged role in superconductivity. At magic angle, it decreases interactions, suppresses superconductivity. A large angle it suppresses the insulating state and allows superconductivity to emerge. So could be there's some, well, I would say it's maybe pyromechanism driven by interactions. So maybe it's pointing towards unconventional superconductivity. But I want to say that STO actually now is a very nice platform to twin screening in situ for correlated systems. For example, if we have other correlated systems like Mori TMDs or rhombohedral layer graphene. Okay, so to screen or not to screen, this is similar to Steve's public lectures. It's like now, of course, we can say yes, right? Both. Since we are in the quantum system, we don't have to pick one or another. We're going to do both. Okay. Yeah, to twist or not to stick, both. Yeah. Okay, so let me just say that. So Allan, happy prime number birthday, and maybe you'll have many more to come. And this is so there's a limerick to Allan. Allan MacDonald, really bright in physics, he soars to new height with Hall effects anomalous and twistronics marvelous. He bends quantum to his light. Full disclosure, I conceived the project with ChatGPT. One more, I want to say this, play this. This will also tell the student. No, whoops. Okay, so thank you very much.
Thank you, Jeanie. Any question for Jeanie? Maybe Emmanuel first. Yes. Emmanuel. Emmanuel, can you turn on the mic on?
Oh, very nice data. How do you reconcile your results with, I think you mentioned the work by Andrea Young and by, I guess, the Dmitry Efetov, right? How do you reconcile your results with the work of Stevan at Caltech, where they put the twisted bilayer graphene on tungsten diselenide, which has a higher dielectric constant, and they see superconductivity over a wider range and don't see correlated insulators?
Yeah, so that's a good question. I think, well, with tungsten diselenide, well, okay. I think the dielectric constant, I don't know how big it is, probably not as big as STO. And I think this is also spin-orbit coupling. I think they definitely put another twist on there. So I think it is, these are all interesting questions. I don't know if I could answer for that. I think, well, that's why we need more funding to study more. But I will say but in the sample, I will say, since it's in situ in the same sample, I will going to stand by my result. At least this shows that in the screening does seem to, I would say, quite a large influence on superconductivity.
Thank you.
More quick question.
I have the, yeah. Thank you for your talk. And can I confirm at which range of filling factor in your large angle twisted graphene do you see superconductivity, and can it be associated with Van Hove singularity?
Oh, that's interesting. I think I should get back to, I think it's, okay, we have seen, oops, oh, it's gone. But we have seen so this one, I think the one we actually really look at is the around -2. And then there's another pocket, which is also low resistance, but unfortunately, the sample died before we can go to investigate that. And that one is close to +1.
That's a filling factor +1?
Yeah, right.
And
but I should get back to you. I'll verify the numbers.
Does it have a very large range above and below?
No, the range is not.
It's just very, very narrow.
So yeah, the pocket of superconductivity we see is pretty narrow, pretty small range.
Okay,
yeah.
so it might be associated with Van Hove singularity.
Thank you. I think we better move to the next speaker.